Welcome to my YouTube channel, Know About Embedded System. In today's video, we will discuss how to develop an embedded C code for PLL. So guys, you know that already what is a PLL. PLL stands for phase lock loop. So already I have one more video where I have explained in detailed theory part of PLL. You please watch that video. What is PLL, why it is, just all those things I have. Link I'll be sharing in the description box. But in today's video, I'll concentrate only on developing the code for PLL. Before starting the video, if you're a new viewer to my channel, kindly subscribe my YouTube channel and gain the knowledge on embedded system. Let us start the video. PLL, embedded C code for PLL. So guys, you know that already. PLL stands for phase lock loop, and it is used to synthesize a new and high frequency for the microcontrollers. So best in the diagram you can see. So this is my external crystal oscillator, which is giving a 12 megahertz, and here you can see this part. So it is able to generate 384 megahertz. So input is 12, and with the help of PLL, we're able to generate 384. So that means what is PLL? PLL is used to generate a new and high frequency, which is a very constant, or which is very consistent in the its frequency value. Okay, so we will part, and before going to the coding, here you can see some of the equations also we have to understand, because based on the equation we have to configure some parameters in the PLL. So first part of PLL is, here you can see one is called FCCO. You know that what is FCCO stands for. FCCO stands for frequency of current controlled oscillator. We have internal oscillator, nothing but inside the PLL there is a one oscillator that is called as current controlled oscillator. Okay, VCO and CCO, just now we have seen in the previous block diagram, VCO and CCO. So the frequency of that CCO is called as FCCO, and that is having one equation, 2 into M into F input and N divided by N. 2 is a constant, M is a multiplication factor, and F in is the input frequency, and N is a dividing factor. So using this equation, we can reconfigure and we can find out unknown values of M and N as well. Here you can see this is your M and this is your N. So this is the first part. The second part, before entering into the programming, so we have to understand. So what will be the range of your FCCO? FCCO is able to generate high frequency from 275 to 550 megahertz. This is the range where we will get FCCO frequency, and we can configure at a standard value according to our design or according to your microcontroller requirement. In my case, today I'll be concentrating, or I'm going to generate the frequency value of FCCO with a 384 megahertz. I want to design PLL which has to generate 384 megahertz as a FCCO clock. Okay, so this is my second important point before entering into the program. And to design this 384 megahertz, so I have to configure some of the important parameters such as F input. F input, nothing but input crystal frequency, external crystal frequency. I'm taking 12 megahertz because we're supplying 12 megahertz clock to the microcontroller from the external. And dividing factor I'm taking as a 1. And if you calculate M value, if you substitute all this FCCO value, F in value and N value in this equation, and I will get M value as a 16. Okay, so I want to design PLL with a 384 megahertz by considering F input is equal to 12 megahertz and N is equal to 1, that is dividing factor as 1. And if you find out M value with the help of this equation, M we will get 16. Okay, these things we should know before entering into the programming of your PLL. Okay, now, so there are some steps we have to follow here. Those steps I have already mentioned here. Yeah, so this is already a base setup I have already done. Here you can see these are all the macros related to our PLL. I have already defined the macros. What are those? One by one I'll explain. And also in the main code. Here you can see this is my main code. In the main code, what I have done is I'm going to just toggle my LEDs. I'm going to toggle some of the port pins which are defined from P1.19 to 26. 8 port pins I'm going to toggle. Here you can see this is a while of 1, and in the while of 1 I'll be continuously configuring. You can see here. So this is my while of 1 loop. Okay, so in the while of 1 I'll be toggling LEDs, but here you can see the important thing lies here. I have one counter here. This count, every time when I toggle once, the counter will get incremented. Whenever my count reaches to 20, I am going to configure my PLL. Okay, I'm going to configure my PLL. So this PLL will be configured only after 20 counts. Okay, so this I'll explain you when it comes to the coding part. Now coming back to the main code of our PLL. So this is my skeleton code of my PLL here. Yeah, so in this main code, so I have already done base setup. There are some things we have to configure one by one. The first thing is we have to enable the main oscillator and its range. Okay, so we have to enable the main oscillator and its range, and that is available in the, I'll just take you to the user manual here. Yeah, so this is my user manual, and I need to go to, yeah, you can see. So this is my register that's called as a system control status register. Okay, so which is coming under LPC 176 system control chapter. Here some of the parameters we have to understand. Here you can see one by one I'll explain the system control and clock status register. Here the first thing is, since we are going to configure PLL with respect to the clock, we have to select the range. Range should be selected with respect to your external crystal oscillator. So range should be selected with the external. So this is a bit number 4 of your system control register, first point. Second point, here you can see we have to enable oscillator. The second point, we have to enable the oscillator. Bit number 4, we have to select the range. Bit number 5, we have to enable the oscillator, and bit number 6, we have to check whether oscillator is stable or not, whether it is ready to use or not. Bit number 6 is there, not bit number 6 is used to check whether the stable oscillator is stable or not. These 3 points we have to configure as a first setup or a first step of configuration in the PLL. One is a range, one is a oscillator enable, and next one is status. Now same thing, if you come back to the coding here you can see I have already defined the macros for oscillators. The one is a range, bit number 4, one is a oscillator enable, bit number 5, and then one is oscillator status. So these 3 parameters we have to configure. So let us do that. Okay, so how to do? So we have to develop the code for that. So LPC underscore SSE. SSE stands for system control block. Under this there is a register SSES. SSES stands for, again you need to go back to the user manual, system control and status register. SSES stands for system control and status register. So come back here. SSES is equal to, so I need to configure 2 parameters here. One is I need to enable the range. I'll directly write its macro here. You can even write its bit position as well. That's also fine. I'm going to enable the range, that is bit number 4, and then I'm going to enable. This is my first configuration under PLL. So we have to enable the range, and next one is we have to enable the oscillator. Okay. The second point, disable the PLL. So if you want to disable the PLL, so we have to go to the PLL chapter in your user manual. So here chapter number, here you can see this is my chapter number 4. Under that 4.5 you have to go. So in the 4.5, so these are all the different registers of your PLL. You can see one is a PLL control, one is a PLL configuration, one is a PLL status, and then PLL feed. Okay, so one by one I'll explain when it comes to the configuration. The first one is PLL configuration and PLL control. You can see here. So this is called PLL control register. Here only 2 bits we are going to use. The first one is PLL bit number 0, that is called PLL enable, and bit number 1 PLL connect. 2 bits we are going to use. One is PLL enable bit and one is PLL connect bit under PLL control register. Okay, the short form of this PLL control register is PLL con. Okay, so PLL con. So I'll go back to coding here. So I need to disable the PLL. So if you want to disable the PLL, LPC underscore SSE under then PLL C SSE PLL 0. So we have to go for con. Okay, so this is the name PLL. PLL stands for phase lock loop, 0 stands for, there are 2 PLLs here, that is why we have to use PLL 0 here. I need to disable, so that's why I'll just send it as 0. When you send it as 0, when you send it 0, that's going to configure your PLL in a disable, or you can say PLL will be disabled. So after that, what we have to do, we have to give the PLL feed sequence similar to our watchdog timer. So here also we have to assign feed value as a exactly same as our watchdog timer. So here also we have to assign some feed value. It is similar to our watchdog timer. So exactly same, 0xAE and 0x55. So this is my first major step to configure PLL. Okay, so what I did, so I have enabled oscillator range and also I have enabled a main oscillator in the sense external oscillator, then disabled the PLL, then I have assigned the PLL feed sequence. So after this, so important point here is I have to check whether my main oscillator is stable or not. Here line number 23 you can see whether my main oscillator is stable or not. So to do that we have to again use, here you can see bit number 6 of our SCC register, SCCS register. So using polling method, I have to use a polling method here, while negate, I have to use SCCS, I need to use SCCS and then perform AND operation and then check the status here. So this is going to monitor whether the oscillator is stable or not, or else you can directly use bit number 6. Even this also you can use. If you're getting confused, this I'll use this. Both are same. So what is one left shift of 6? One left shift of 6 is nothing but whether my oscillator is stable or not. I have already explained you. Just watch the video once again. Okay, now the first major step is done. What I did, I have enabled the range, I have enabled the main oscillator, I have disabled the PLL, assigned the PLL, and then I have assigned the feed to PLL. Then I'm checking whether my oscillator is stable or not. The first step is done. Now the second step I have to move my second major step. So some 3 to 4 configurations we have to do. Here you can see select clock source from the PLL. So we have to select the clock source, and then we have to use the CPU clock divider. Then we have to configure the M and N value. Okay, now how do you select the clock source? To select the clock source, we have to go for, there is something called clock source selection. I'll just go to here. I'll show you where we have to check the clock source. Yeah, here you can see. So this is called clock source selection. this register, whatever you're seeing, this is called clock source selection. So what it tells, this clock source selection will tell you which clock you want to use for PLL. Here you can see they have given 4 combination here, 0 0 0 1 1 0 and 1 1. 0 0, it is going to select the internal RC oscillator for PLL, or when you give 0 1 combination, it is going to select your main oscillator, nothing but external oscillator, and whenever you give 1 0, it is going to select RTC and so on. Okay, but our intention is to select 0 1 combination, nothing but 1. So this is called clock source selection for PLL. So try to understand here. The clock source register contains the bit that is going to select the clock source for PLL. Okay, so now I'll go back to the coding here. I need to select the clock, so I need to develop the code for that. Same thing again. I have to use LPC-SC. Now I have to type the register CLK, that stands for clock, SRC, SRC, SEL. So this is a name which they have defined in the microcontroller register list, CLK SRC selection. So that stands for clock source selection. I'll just assign as 0 1 here, or you can directly say 1. So when you say that, that's going to select clock source to the PLL. Okay, that's the first point. Second point in the configuration is I have to select clock divider for CPU clock here. That is also similar, LPC underscore SC here. So there is something called C clock, is there, C clock, SRC, SCL. So this is there, no, CPU clock. This is called, okay, CFG. Okay, so here I'll assign as 3. So what it says, here, you try to understand here. Line number 26 is clear. I'm going to select the source, clock source for PLL. Yes. Okay, now this is perfect. Select main oscillator as a clock source for PLL, line number 26. Line number 28, what it says. So I'm going, so there I have already told you, clock source for your CPU clock. CPU clock in the sense for CPU also there will be a clock. So that we have to do. So what it will do, so there is a small equation here. The CPU clock is equal to, very simple it is. Here you can see. When I assign CPU clock value as 3, this value will be divided with respect to FCCO, right? So we are going to configure FCCO with a 384 megahertz, right? So 384 megahertz we are going to configure. So 384 divided by 3 plus 1. So it is going to understand like this. So FCCO divided by, so your so this is the equation. See, FCCO frequency divided by CPU clock configuration plus 1. So CPU clock configuration I have assigned as 3. FCCO we are configuring as 384. 384 divided by 3 plus 1. So that is going to generate 96 megahertz. So that means CPU clock will be able to generate with 96 megahertz. So this is my second major step to divide the CPU clock frequency. Okay, then actual configuration for PLL, we have already calculated M is equal to 16 and N is equal to 1. So we have to minus 1. So whenever you're getting M is equal to 16, there is a bit called as MSEL and there is also a bit called as NSEL. I will show you those bits. So always MSEL and NSEL will be always minus 1 of your M. So M is equal to 16, MSEL should be assigned with 15, and N is equal to 1 and NSEL will be 0. So where these things available, I need to go back to user manual here and then come back to your PLL. I'll show you where we have to configure. So we have to configure in a PLL CFG register. There is a register called as PLL CFG. So come down here. Here you can see. So this is the register, what I'm talking about. PLL 0 configuration. PLL 0 configuration. Here I already told you. So bit number 0 to bit number 14. MSEL bits and NSEL bits bit number 16 to bit number 23. Okay, so always do remember, always MSEL is equal to M minus 1 and NSEL is equal to N minus 1. That is the reason we calculated 16 and 16 minus 1, 15 we have to upload in the MSEL, and NSEL we have to upload 1 minus 1, it is 0. I hope you're clear with the MSEL and NSEL. So this we have to configure in a PLL configuration register. So come back to coding here. So in the coding, as usual, LPC underscore SC PLL0 CFG PLL0 configuration is equal to, so it's going to, I'm going to load 0x 0f here. Yeah, so this is 15 is nothing but f, so MSEL bit is 15, nothing but f. N is equal to z, NSEL is equal to 0. I'm not going to configure here. Okay, so next one, enable, I need to enable the PLL. So if you want to enable the PLL, just you need to assign it as 1. So this is going to enable your PLL. Okay, so and then I need to assign the feed signal here. So as usual, every time we have to assign the feed signal. Whenever you do the configuration for PLL, we have to assign the feed signal. So feed signal is also done. So now I have to check whether PLL is locked or not. So to check that, here you can see line number 37. So line number 37, I need to check whether PLL is locked or not. So what do you mean by PLL locked or not? Locked in the sense whether your PLL is able to generate a desired frequency or not. What do you mean by locking a PLL? Locking PLL means check whether PLL is able to generate a desired frequency of 384 megahertz or not. So if it generates, then PLL will get locked. To check that, again we have to come down here. This is a control register, configuration register. This is called PLL status. Here you can see there is a P lock bit is there. This is going to reflect whether lock state. So when it is 0, it is not locked, and when it is 1, the PLL locked into requested frequency. So this is called PLL lock state. Try to understand the statement what I have highlighted here. So PLL lock state, if it is 1, then the PLL is able to generate with a desired frequency, and when it is 0, it is not. And this is available in a PLL status register bit number 26. So we have to check bit number 26. Come back to the coding here. Here you can see I have already defined PLL underscore lock. You can use the same macro. Use polling statement here, while negation. You can use PLL status. Instead of feed, you can use PLL state and operation with, you can use directly or you can use a macro, anything is fine. In order to avoid confusion, I'm using the number here. Or you can use even this as well, PLL lock state. Okay. You can use this as well, PLL lock state. So both are fine. So whichever comfortable for you, you can use it, or else I'll use PLL lock state. Yeah. Now this looks like fine. Now the second major step is also done. So here I'm check whether. So till now, second major step is completed. Configuration of major PLL and also checking whether PLL locked or not. So the last step is I have to enable the PLL and connect it to the CPU. So very simple steps in order to do that. So what I have to do, very simple steps I have to do. So that is PLL. So already I have enabled here. So you can see PLL enable, that bit I'll use, or you can use one left shift of 0, that is also fine. Okay, so I'm going to use enable bit here. So instead of to avoid the confusion, I'm going to enable PLL and then I'm going to enable PLL connect. So both, once the PLL is locked, I have to enable and then I need to connect my PLL. PLL connect is nothing but bit number 1 here. So I'll just, yeah, here. Yeah, so now we're fine with most of the coding is done. Just last step is I have to assign the feed value. That's it. So when you do this configuration, so this function will generate 96 megahertz frequency for your CPU clock, and peripheral clock will be 24 megahertz. Function is done. Okay, first we'll check the output, later I'll come back and I'll explain what we have done in the coding part. Yeah, so now so let us compile the code. So before checking the output, as I told you, so what we have to observe, I have already explained what to observe. So before PLL configuration, CPU clock will be at 4 megahertz, peripheral clock will be at 1 megahertz, and USB also will be 1 megahertz, and probably USB clock also, there is a small correction, USB clock will be at 384 megahertz only, because we are not configuring USB clock. After configuration of PLL, FCCO 384, CPU clock 96, peripheral clock 24, and USB clock at 384. So these things we have to observe. Okay, so now let us compile the code. Okay, now this is fine. I'll enter into debug window. So I have given count value as 20. So after count value as crossing the 20, so I'm able to generate CPU frequency. Okay, these are all the different clock values, yeah. So this is your system control. This is your clock. See, this is what I told you to observe. This is a CPU clock frequency, and this is, you can see here, USB clock, and these are all your different peripherals. Usually peripheral clock will be divided by 4. Peripheral clock is equal to CPU clock divided by 4, and these are all your phase lock PLL configuration, and this is your system control and status register. Okay, and this is your watch window. Here I have already uploaded the count value. So now I'll run the code here. Observe what is going to happen. So observe here, the count is running, and observe here the CPU clock is running at 4, and here the USB clock. Yeah, now you can see here. So what happened now? The USB clock is running at 384 megahertz, and you can see the peripheral, all the peripherals are running at 24 megahertz, right? So all the peripherals are running at 24 megahertz, and CPU clock is running at 96 megahertz. USB is also running at 384 megahertz, right? Yeah, so this is how, and you can see the PLL input, the PLL is able to generate this frequency, which we have calculated already, that is 384 megahertz. Please click on like button and subscribe to my YouTube channel.